Richard Price, your host, and also the founder and CEO of academia.edu. So yeah, I get really excited to dig deep into academic ideas. But remember, I'm here to present and explore papers neutrally with you as my co-investigator. I'm not endorsing the arguments or taking a side here. I just love sharing what's out there in the huge world of academic research and seeing what insights we can take for ourselves. Today, we're diving into a paper by Dr. Trajan Terek, who, by the way, is a neuroradiologist and an independent researcher, also the author of something called the Fractalon Unified Theory. And fun fact, ChatGPT, yes, OpenAI's language model, is credited as a computational physics co-author on this one. How wild is that? AI as a co-author. Maybe I should try that for my next meeting notes. Anyway, the paper's title is Reflected Light Interpretation of the Double Slit Experiment within the Fractalon Unified Theory. Pretty hefty, right? Let's unpack what's actually going on. So you might remember the double slit experiment from high school physics, the one where light shines through two tiny slits and creates that classic pattern of light and dark stripes on a screen. This experiment is, well, legendary for showing us the weirdness of wave-particle duality in quantum physics. Light doesn't just act like a wave and a particle, it sort of acts like both at the same time, which is, let's just say it's always made my brain hurt a bit. But Dr. Terek's paper presents a totally fresh perspective. Instead of the interference and diffraction story most of us have heard, he says, actually, maybe those patterns are a geometric outcome of multiple light reflections that happen in this sort of structured, lattice-like ether that surrounds all matter. Why is this significant? Well, for one, if light patterns come from reflection in an underlying structure, not interference, that would upend how we interpret a central experiment in physics. That would mean maybe there's more order and geometry hidden in what looks like randomness. Some folks love that idea, others, not so much. Okay, let's talk about the methods and findings. Dr. Terek didn't just speculate, he ran actual experiments. He set up two thin cylindrical mirrors, think metal wires, parallel to each other with a tiny gap, and shone red and green lasers right through them onto a screen a couple meters away. He then took super close-up photos using an iPhone, which is just, something I'd love to see on Instagram. Honestly, here's the crux. The reflection model predicts distinct spacing for reflection bands depending on the wavelength. So red light with a longer wavelength should give wider spaced bands, and green with a shorter wavelength should produce bands that are closer together. And when Dr. Terek measured